Welcome to our third Lunch and Learn session with Neural Magic. And today we're going to try to talk a bit more about second-order methods for pruning. My name is Eldar Kurtić, and I'm a research ML engineer at Neural Magic and Institute of Science and Technology of Austria. Before we dive into this topic, I would like to show you these three links here. So the GitHub page from Neural Magic, our Twitter account, and our Slack community. And I would highly encourage you to join our Slack community because we have a lot of people there trying to compress different models on different data sets. And our team is as well engaged quite actively in discussions there, so you can quickly get support on all the problems that you might stumble upon during your projects. So let's dive into the topic for today. The agenda for today will look as follows. So first, we're going to cover some background on pruning. So we are all on the same page regarding the terminology here. And then we'll cover second-order methods for pruning. And we will mostly focus on three of our recent papers on this topic. After that, we'll try to show you some results. So some kind of accuracy versus sparsity trade-offs that you will be able to achieve with these methods while compressing your models. And then we'll also show you how to deploy these models to get some practical inference speedups on CPUs with our deep sparse engine. And in the end, we'll also present some intuition about why do we think that these methods work in practice. At the end of the presentation, we'll also point you and provide some resources on our open source code and open source model repository, which you can use to apply these techniques on your own models and on your own data sets as well. And I think we will have some time for a brief discussion and Q&A session in the end, just in case you have some questions to ask. So what is pruning in general? So by pruning, we refer to the process of taking a deep neural network and trying to cut or prune away weights from it. And by pruning away weights from it, we mean literally putting zeros inside of the weight matrices of this model. And later on, the more zeros we have in the model, we can utilize that to get practical speedups during the inference. So there are kind of two ways to classify pruning methods in general. The first classification that we can do is based on the pruning mask. So given a weight matrix, so standard kind of torch and a linear layer, we can impose kind of the first type of the pruning is unstructured pruning. So if we impose the unstructured pruning mask, this means that we are kind of randomly pruning weights in this network without any concrete pattern inside of that. The second type is a semi-structured or block pruning. And here we are trying to zero out weights in some predefined shapes. In this case, we have blocks of 2 by 2. And the last type is the structure pruning, where we are trying to completely remove rows or columns from these weight matrices. The second type of classification is based on the pruning criteria. So here we have zero first and second order methods. By zero order methods, we consider all methods that are using only magnitudes of weights for pruning. And one such example is standard magnitude pruning, which actually just takes prunes away the weights with the lowest magnitude, with the smallest magnitude. Then we have first order methods, and these are the methods that are trying to leverage gradient of the loss function while fine-tuning a model on a specific task. One example here is the standard movement pruning, which actually tries to prune weights that are moving towards zero while fine-tuning the model on a specific task. And then in the end, we have the second order methods. These are the methods that are trying to leverage the curvature of the loss function. And some of the methods that we will cover today are on this topic will be mostly focused on unstructured and block pruning, and they will try to leverage second order methods to achieve this. And here we will cover three of our recent papers called Wood, Fisher, MFAC, and Obert. So before we dive into these concrete methods for pruning, we would just like to point you to some kind of interesting observations regarding pruning. So why should you care about pruning in general? So the first kind of obvious answer to this question is that the more zeros we have in our model, the less memory we need to store the model on a disk. And the second kind of less obvious to most people is that the most zeros we have in the model, the better and faster inference we can get on a specific, in specific sparsity aware inference engines. In our case, this is a deep sparse engine, which can leverage sparsity to provide you kind of GPU class performance on commodity CPUs. Here on this plot, we are looking at the accuracy versus speed up of the standard BERT-based model on the standard question answering squad dataset. And here we, with these 3 gray dots, we are looking at 3 different variants of this model with 12, 6, and 3 layers. And all these models are dense models running in the standard Onyx runtime. What we can see here with these blue graphs, so we actually tried to prune these models up to 70, 80, and 90% sparsity. And then we are running inference with these models in our sparsity-aware deep sparse engine. And kind of the first observation that we can see here, so if we try to compare these kind of data points on a horizontal line, we can see that for the same level of accuracy, by just imposing a certain degree of sparsity on the model, we can get models that are from 2 to 4 times faster than the corresponding dense model running in Onyx engine. And these models are obtained with the simplest magnitude pruner. And towards the end of the presentation, we will see that we can significantly improve upon these results by leveraging our second-order pruning techniques. The other kind of interesting observation here is kind of comparing these data points on a vertical line. So, for example, without any kind of pruning, if we have an application which requires some specific inference speedup, let's say in this case 250 items per second, the best thing that we could do without pruning is take a smaller model, try to train it as good as possible, and then deploy it in the Onyx runtime. However, the main problem there is that it's going to be really hard to achieve competitive accuracies with the smaller models. And what pruning actually enables us to do is to take a much larger model, train it until we reach the desired kind of competitive performance, and then we can try to prune it as much as possible such that we preserve the accuracy. And in this case, for example, we've been able to prune the 12-layer model up to 90% sparsity while recovering the accuracy, and we still have the same inference speedup as the dense 3-layer model running in the standard Onyx runtime. So now let's dive a little bit more into the second-order methods for pruning. So kind of the timeline of development of these methods started with the 2 seminal works called Optimal Brain Damage and Optimal Brain Surgeon. Both of these papers approach the problem and try to prune the weights from the network by trying to approximate the curvature of the loss function. Our 3 papers, Wood, Fisher, and MFAC, and Optimal Brain Surgeon, are built most on top of the Optimal Brain Surgeon framework, and they're trying. The main idea was to adapt this framework and make it more efficient and scalable for the neural networks that we are using these days. So with the model sizes that are ranging from 10 million to 100 millions of parameters. On the theory side, we can first start with the Optimal Brain Damage and Optimal Brain Surgeon frameworks to explain kind of the theory background behind these techniques. So we first start from a well-optimized dense model. In this case, we represented with the WV star, and here we consider all the weights of the network as a 1D dimensional vector. So we flatten all the weights in one vector, because the iterations will be much simpler in that way. And then we aim to find the sparse version of this model. So we are trying to put as many zeros as possible in this vector while preserving the accuracy of the dense model, which is our baseline. And the approach actually starts by expanding the loss function around these well-optimized weights with respect to the sparsified weights. So this is the standard second-order Taylor approximation that we can apply. And the first thing that we can observe here is, given the fact that we are starting from a well-optimized dense model, we can drop the first-order term here because the gradients are close to 0. So this is kind of a safe approximation that we can do. And then we can rearrange these terms a little bit, push this loss on the left side, and get the following expression. This quadratic form here, which is a positive semi-definite form, gives us an equation to evaluate the loss increase due to pruning. So what would be the effect if we prune away some weights from our network? However, there is one problem. So this is the first problem that we arrive at in general in this second order pruning pipeline, and that's this dependency on the hashing. So the first problem that we try to solve is how to compute the hashing of the model. As we all know, this is a D by D matrix, which is extremely huge, and we cannot compute it because this is a matrix of second order derivatives. We would need to do forward backward pass for each one of them to compute, which is infeasible for networks that we are working with these days. So the OBS framework proposed an approach where we are approximating the hashing with a dampened empirical Fisher information matrix. And there is the theory that says that if our model is in a well-optimized state, this approximation is reasonable. Later on, we will also show you some plots which should kind of confirm this approximation. And this empirical Fisher information matrix is literally just the average of outer products of gradients. So we calculate these rank 1 products of gradients, and then we add the small dampening term on the main diagonal to make this matrix invertible. Then, if we go back to our pruning problem, so our main goal is to identify a weight whose removal would incur a minimum increase in loss. So we can formulate this as an optimization problem. So we are trying to minimize this loss increase given by this quadratic form such that some specific weight WVK is set to 0. And now, if we solve this problem with the method of Lagrange multipliers, we will arrive at the following equation. And this equation gives us an optimal weight update that we have to apply on our model. And by applying this optimal weight update, we would cancel out this kth weight in the network. So we will zero it out completely. But kind of a side effect of this update is that we will also at the same time update the remaining weights in the network. And later on, we will see that this update is kind of the crucial part of the for good performance of second order methods, because it allows us to compensate for the loss increase that will happen after we zero out some specific weights in the network. So now if we take this optimal weight update, we plug it inside of back to our objective of the optimization. So kind of calculating back the loss increase due to pruning after we apply this optimal weight update, we get this following expression here, which is called the saliency score. And by this, so we actually we have a way to measure the effect of pruning a specific weight WVK. So what we can do now, we can take all the weights in our network, compute this score for each weight, and then prune away the ones with the smallest score, because that means that they have the minimal impact on the loss of the one. And this kind of story looks good and fine, but there is one problem, and that problem is this inverse Fisher matrix that appears in the expression for optimal weight update and for the saliency score. So even for a network that is as small as ResNet 50, this takes more than 2 petabytes of data. So because the ResNet 50 has roughly 20 to 25 million parameters, and then storing the entire inverse Fisher matrix would take 2 petabytes of data, which is not feasible for the hardware that we have these days. So the first solution to this problem is proposed in our good Fisher paper, which stands for the efficient second order approximation for neural network compression. And the solution is to apply a blockwise approximation of the hashing along the main diagram. So instead of taking into account the entire D by D matrix, we just take into account some specific blocks along the main diagonal, and the size of these blocks usually depends on the memory resources that we can leverage for training pipeline. So now that we have a way to actually store and operate with this inverse Fisher, with this Fisher matrix, we also need a way to invert it, because all the equations on our previous slide were dependent on the inverse of the Fisher matrix. So a nice trick that we can apply here is relying on the fact that the matrix we want to invert is a sum of rank 1 matrices. So given by this empirical Fisher approximation. And in this case, we can make use of the Woodbury-Sherwin-Morris trick, which actually gives us an exact way to compute an inverse of a matrix A plus the rank 1 update given by this outer product of 2 vectors. which in our case are gradients. So by applying this formulation here, we can actually compute the inverse efficiently and also in a very stable way by considering one gradient at a time. So if we now take our expression for the Fisher information matrix and we plug it inside this Woodbury inversion formula, we will get a recursive formulation which we can unroll and arrive at this specific expression here. And this expression actually gives us a formula to calculate the inverse Fisher matrix given a set of m gradients. So what we would do, we would take our network, do several forward-backward passes, take these gradients, and then compute these blockwise inverse Hessian vector products. And this is kind of the main part of the Wood-Fisher paper, where we actually showed that even with this blockwise approximation, we can get extremely competitive results and outperform first and zero-order methods. The next problem that we wanted to tackle is this blockwise approximation. So the main kind of point, the main question there was if we can get around this blockwise approximation and find a way to approximate the full Hessian. So this is now the topic of our second paper called MFAC, which stands for the efficient matrix-free approximation of second-order information. And here we start from this expression of the inverse Fisher matrix that we have introduced before. So as we know, so now we have these two, we have the sum of these outer products of vectors, and in the original form, this would be extremely huge matrix. So D by D matrix. So those are these 2 petabytes of data that we would need to store even for ResNet 50 model. But then if we take a step back and try to look at where do we actually need to use this inverse Fisher matrix in our entire kind of pruning pipeline, we will notice that it appears in the expression for optimal weight update. And here it appears here it appears in a product with this basis vector EK, which actually just extracts the kth column from this matrix. So now, if we plug this formulation for inverse Fisher inside the optimal weight update, we pull inside this product with the basis vector EK. We can see that this first part is the same. So this is still the vector. This part in the denominator is a scalar. But now this part actually here is a dot product between 2 vectors, which gives us a scalar. And now this entire kind of expression for the optimal weight update collapses to a linear combination of vectors of size D, where D is the size of our model. And this is kind of the main idea and the main topic that we explored in the MFAC paper, where we presented a few additional tricks on how to compute this efficiently and how to also query elements of the inverse Fisher, because we also see here that in the denominator we need to get the kth element from the inverse Fisher, so the kth element on the main diagonal. So the main idea there is we also applied the same trick by multiplying with the basis vector from the left side, and then we try to extract the corresponding element. And with some kind of pre-computations, we can compute this quite efficiently for pruning. One of the problems in this specific setup is that we still, in order to execute this efficiently, we still need to consume some moderate amount of memory, which was the main reason why we applied our pruning techniques mostly to computer vision models like ResNets, mobile nets, YOLO models, and so on, which are usually not exceeding like 30 to 40 million parameters. But then we wanted to see if we can make this approach a little bit more scalable and more kind of memory efficient. And if we can try to expand it to cover the NLP domain, so natural language processing domain, and if we can try to prune some language models like BERT-based, BERT-large, which have hundreds and for example 100 or 300 million parameters. So the next question in addition to that was if we can actually extend this standard second-order pruning pipeline from unstructured to semi-structured pruning, where we can also cover pruning of blocks of weights or some specific NM shapes. And the last question that we also wanted to see to get an answer to is actually the compound compression pipeline. So if we wanted to see if we can actually combine the different compression techniques like unstructured pruning, semi-structured and structured pruning with quantization to get extremely compressed models, which we can run quite efficiently on any kind of hardware. And these three questions are the main topic of our third paper called the optimal BERT surgeon, where we, instead of proceeding with the MFAC approach, where we try to approximate the entire Hessian matrix, we go back to the Wood-Fisher approach. So we are doing a blockwise approximation, and then we introduce a few simple optimizations where we are able to store just one gradient at a time, which makes this approach a little bit more scalable to large language models like BERT here. One question that we should also clarify here and emphasize is this flexibility to impose different types of sparsity masks. So far we've been concerned mainly with the unstructured sparsity masks, but different types of inference engines can provide us kind of different speedups, but they all require some specific sparsity pattern in our network. For example, the block sparse GPU kernels from OpenAI, they can provide us some speedups on GPUs, but they require specific shapes of blocks of zeros that we have to impose on top of our model. And these blocks are ranging from 8x8 to 32x32. Then NVIDIA also has sparse tensor cores, but in order to get any kind of speed up there, we need to prune our model in a 2-fork pattern, which means that in each block of 4 weights, we need to have 2 zeros and two weights, two standard kind of dense weights. Then we also have VNNI instruction set, which can provide us some speedups, but we need to prune our model in a block 4-way, which means that for each consecutive set of or group of block or actually block of 4 weights, we keep it dense, or we have to prune it completely. And then at the end, we have our own inference engine, which is a sparsity-aware CPU engine called Deep Sparse. And here we actually support any kind of sparsity. So any kind of sparsity that you can impose on top of your model, you can leverage that for actual speedups in the Deep Sparse. So now let's take a brief look at some of the results that we've been able to achieve with all these methods so far. So with Wood-Fisher, MFAC, and the optimal BERT surgeon. So here we are looking at the one-shot pruning of the ResNet 50 model, which has been trained on the ImageNet dataset. And we are looking at the top 5 accuracy relative to the different sparsity targets. What we can see here is that Wood-Fisher and MFAC methods they improve significantly upon prior methods like magnitude pruning, layer-wise and global, and as well as the layer-wise OBS framework, and especially at higher sparsities. And one thing to kind of emphasize here is that the higher sparsities are the regime that we mostly care about, because most of these inference engines can provide us speedups, but they require higher sparsities than 50%, for example. And this is actually where the main difference in different pruning techniques starts showing up. The next set of results that we will look at represented as a gradual pruning setup. So gradual pruning setup is a setup where we are iteratively pruning and fine-tuning the model until we reach the desired sparsity target in the model. And here we consider MobileNet and the ResNet 50 model on the ImageNet dataset. This is kind of a standard benchmark for computer vision pruning. And here we compare Wood-Fisher and MFAC approaches with the global magnitude pruning and STR pruning. And as we can see here, both of our second-order methods are able to improve roughly 2 or 3 points in top 1 accuracy relative to prior approaches, and this actual improvement is quite significant at these specific high sparsity regimes, like 90 and 95% sparsity that we are considering here. The next set of results is about natural language processing domain. So here we are considering the kind of standard benchmark, which is pruning the BERT-based model on the question answering squad dataset. And here we are looking at results from the gradual pruning setup, where we iteratively prune and fine-tune the model until we reach the target sparsity. And here we are looking at the F1 score relative to the two different sparsity targets. And as you can see, with the optimal BERT surgeon pruner, we can improve significantly upon prior methods, which are first order methods like movement pruning and as kind of zero order methods like prune once per all and lottery ticket hypothesis and the sparse BERT. One interesting observation from this graph is that the OBERT paper was the first one that showed that we can actually prune language models up to 90% sparsity while still recovering the while fully recovering the accuracy of the dense model. So only with the 10% of the weights in the model we can have quite competitive accuracies. So now that we have a way to prune models to high sparsities and with high accuracies, the next kind of logical setup would be to try to take these models and deploy them in inference engines. In our case, we are trying to deploy our models in deep sparse, which, as I mentioned before, is a sparsity-aware inference engine, which can provide us quite good speedups on CPUs. Here we are looking at the Resonance 50 throughput performance on a deep sparse engine and relative to the standard Onyx runtime. If we compare these models, so starting from bottom to up, we can see that in the Onyx runtime, if we would take the standard dense Resonance 50 model, we would get roughly 320 images per second. Now, if we take the same model and we deploy it in the deep sparse engine, we can get some small improvements. But then, if on top of this model, we apply pruning up to 95% sparsity, which these days we can do with a minimal impact on accuracy, we can get roughly three times faster model. And then if we apply in-stage quantization on top of that, so now we are combining pruning and quantization, we can get additional roughly 2 or 2.5x. And in the end, by compounding these techniques, we can get roughly 8 times faster model than what we would have to set on by just using the standard Onyx runtime with the dense model. The next set of results that we can look at are the results from our optimal BERT surgeon paper, where we also did some kind of compound compression, an approach where we applied structure pruning, semi-structured or block pruning, and quantization on top of these models. And then we wanted to visualize the trade-offs, that can give us kind of a relation between a magnitude of improvement in the inference speed and in the model size compression, based on the level of accuracy that we are willing to drop relative to the dense model. So here, if we look, for example, kind of at this 99% F1 recall line, we can see that if we allow our model to drop roughly 1% in accuracy relative to the dense baseline, we can get a model that is roughly 10 times smaller and roughly 8 times faster. And then if we allow a drop of, for example, 3% in accuracy, we can get models that are 15 times faster and 15 times smaller than the corresponding dense baseline. One thing that I would also like to point out here is that these results are from a few months ago, and they're already outdated because we are actively improving our pruning pipeline. So you can go now on to our sparse zoo and find models which have even better performance than the models that we are showing here. And then in the end, we'll just briefly show you kind of two main points, which are kind of like our intuition why these second order methods work in practice. The first one is explored in the Wood-Fisher paper, where we try to see the similarity in the structure of the true Hessian and the empirical Fisher approximation Here we have to consider super small models, for example, just tiny 3-layer CFARnet on the CFAR10 datasets, because computing the full Hessian is quite expensive. So here on the left and on the right side, we compare the structure of the Hessian and the empirical Fisher matrix. And what we can see here is that they're pretty similar in the structure, and the only difference is in the scale. And this scale doesn't matter much for our specific pruning use case because we are comparing these weights relative to each other. So this should not affect our results as much. And this is what we also showed in the paper. The second point so kind of the second advantage for second order pruning methods is the fact that besides pruning, so besides setting some weights to 0, they give us exactly a formula to update the remaining weights in our network to compensate for the loss that will happen during this pruning step. And one nice way to visualize this and see the effects of this specific weight update is by looking at this plot here, where we applied a gradual pruning on top of the mobile model trained on the image of the dataset, and we are looking at the top 1 accuracy, how it evolves over time, while we are pruning the model until we reach the 89% sparsity. These sharp drops that we can see here represent our setup where we train the model, and then we evaluate the model immediately before the pruning step and immediately after the pruning step. And that's the main reason why we see these huge drops, because this gives us a way to visualize the effect that pruning had on the top 1 accuracy of the model. And we can see that with Woodfisher and with MFAC, these drops in accuracy are significantly smaller than the drops with the magnitude pruning. As you can see, for example, with the magnitude pruning, even at 71% sparsity, the model always collapses to 0 accuracy, and then the optimizer has to compensate for this drop during the following fine-tuning phase. And as we can see, so even if we allow the final kind of sparse models to train for long enough, for example, 8 epochs, the optimizer still cannot compensate enough for these drops in accuracy, which ends with these kind of highly accurate Woodfisher and MFAC models relative to the models that global magnitude approach produce. So if you would like to apply any of our techniques, or if you would like to take a look at our code, we have open source the code for make sure all these techniques that we have described today. So MFAC, Woodfisher, and the optimal BERT surgeon are currently integrated in our sparse ML library. And this is our library, open source library, which you can integrate very easily in any project. So you need just like 2 or 3 lines of code, and you can get these state-of-the-art pruners kind of for free. If you don't feel like gradually pruning your models from scratch, I would encourage you to also check Sparse Zoo. This is our open source model repository where we are actively pushing some new sparse and quantized models, and you can just use them and maybe do the transfer learning on your specific data set, and then make use of the sparse engine to leverage these highly compressed models to get some practical speed ups on CPUs. One kind of cool thing about Sparse Zoo is that we are also open sourcing all the recipes for pruning and for quantization of all these models. So you don't need to start from scratch. You can reuse our own recipes, which our team kind of carefully crafted, and you can just adapt them to your own specific setup. And I think with that, we can finish the presentation. If you have any further questions, I highly encourage you to join our Slack community, where we actually are actively engaged with people with our kind of community who's trying to compress these models, and then you can quickly get support from our team as well. I think now we can do a brief discussion and Q&A session in case there are some questions in the chat.
Yep, Eldar. So we have one more. We've had quite a few questions come in, so it's been great. One more that just came in is, what is the current best one-shot pruning method?
So for one-shot pruning method, it depends on the scale of the model that you're looking at. If you're looking at the models like ResNet, BERT, Base, BERT, Large, and so on, these techniques, so second-order methods that we presented today, are state-of-the-art to the best of our knowledge. But if you are looking to upscale, scale up the pruning to a billion-sized models, so for example, GPT-style models, we would probably encourage you to take a look at our paper called Sparse GPT, which can actually do this in a kind of more efficient way at that scale. Because one thing that you should consider here is that second-order pruning methods depend on the gradients. So you need to have a way to compute the gradient of your model. If you cannot compute the gradient, then you cannot do this kind of curvature approximation. And for these billion-sized models, it's quite hard to compute the gradients.
Thanks, Eldar. And one more thing that I'll add on to that is the next webinar or the next Lunch and Learn that we're going to be putting out, or I should say Learn with Neural Magic, so Sasha doesn't get mad at me for branding. We'll be actually covering our OBC and OBQ algorithms for one shot. So definitely stay in touch for that one. That one is coming up at the end of the month. And then we have another question coming in. I might have missed it, but when performing these pruning techniques, is the percent of pruned neurons homogeneous and equal across each layer? Or do you see a consistency of, say, shallower neurons are more likely to be pruned?
Yeah, so this is a good question. So like generally when we are trying to prune the models, there are kind of two parts. The first part is trying to figure out the sparsity profile. So how many neurons per layer you want to remove. Kind of the standard way is to just do it uniformly across all layers. But the second-order methods that we discussed today are able to actually compute this profile for us, because we consider and we rank all the weights globally. So, for example, we can take all the weights in one vector, and then we allow this second-order approach to actually to figure out how to allocate the sparsity per layer, such that we preserve the accuracy of the model. I hope this is the answer that you've been looking for.
And then we have another one that says, when does empirical Fisher approximation for the Hessian not hold?
Well, so the theory says that this approximation holds only for the setup where we have a well-optimized model. So if we are in a local optimal, then this approximation holds. However, one thing that we have noticed, and you can also see it in the NFAC paper, is that we can also apply this similar approach to the optimization. So where we can where we are trying to kind of compute the inverse Hessian vector product in the context of the natural gradient descent. So we are using this inverse Hessian as a preconditioner to the gradients. So this is like a setup where we are actually trying to optimize the model. So it's not in a fine-tuned state, but the approximation still works fine. So yeah, that's kind of one mismatch that we haven't noticed. But in general, your model should be fine-tuned before applying the pruning step.
And then we have another one. Have you compared to any GPU benchmarks with an optimized pipeline? Pruned quant plus TensorRT.
Yes, I think we have some results on this in some of our blogs, right, at the Neural Magic website, Mark. But I'm not sure exactly which ones. So I think it should be worth checking there and maybe see.
Yeah, but yeah, definitely. Yeah. Oh, sorry, go ahead, Eldar. Yeah, just gonna say, yeah, definitely check out, as Eldar has said, check out the blogs and other resources on our website. Also, we just launched our new MLPerf results, where we do compare to actually the numbers coming out from NVIDIA for their most optimized TensorRT pipelines. And we have any works that you are aware of that has block sparse approximation of the full Fisher?
Not really. So you can apply. So in the OBERT paper, we show actually how to do this kind of block sparse approximation. So you can use it to impose this block pruning mask. But if you want to consider the full Fisher, then you would have to go back to the NFAC approach, which does this in a matrix-free way. So just kind of combine these two parts of the papers.
And then a quick question on if the sparse GPT code is available.
Yes. I think we have open sourced this. You should check the paper. I think the link should be there. If it's not, you can ping me somewhere on Twitter or on Slack, and I'll point you out to the code. But I think it should be out now.
And then, have you attempted to use these methods for structured pruning? If so, how did they perform?
Yeah, so we haven't tried to do the full structured pruning here. So by structured here, I mean in sense of like we are removing completely rows or columns or complete layers of the convolutional layer, because one of the problems there is that we need to specialize the approach, because if we start cutting the rows and columns of these matrices, then the modules in the model will not be compatible, right? If we cut one row from one layer, then we would need to also compensate for this in the different layers. And for this, we have a different paper which tries to tackle this part for language models. It's called ZipLM. So hardware-aware structured pruning for language models, and it's currently on archive, so you can look it up. Because in that setup, you actually have to combine kind of few layers together in order to get a valid kind of shapes of these layers. So then the matrix multiplications are valid. But we are applying kind of an extension of the OBC paper that Mark mentioned before, just to the structured case.
And then another question, could you please explain what block 4 sparsity is, the one you mentioned when you explained VNNI?
Yeah, so block 4 sparsity means that, so if we take our, let's say one layer of a network, so one weight matrix, for each kind of consecutive block of 4 weights, we keep it either dense or sparse. So we have 4 weights, then 4 zeros, 4 weights, 4 zeros, and so on. So that would be this block sparse pattern.
Great. I think that's everything. Any other questions from anyone? All right, great. I think we can call it there. Thank you, Eldar, for presenting, and thank you everyone for joining in.
Thank you. See you, bye.